Okay, we're going to go through and just do some more examples of variation of parameters. And the reason we're doing more examples is because it takes a long time to do these things. It's kind of weird and seems a little bit arbitrary. So just seeing more of it hopefully will help drive home what's going on. So the first example we're going to look at is t squared y double prime minus 2t y prime minus 4y is log of t. And the first thing we should notice here is that this looks like a Cauchy-Euler equation on the left. So trying to make a guess here, what kind of function is going to give us log of t is going to be really difficult. So for that reason, oh, and also it's not homogeneous. So for that reason, we're going to look at variation of parameters is what we're probably going to do. So regardless, the first step is the homogeneous solution. So for the homogeneous solution, and the reason we're doing this is because this is a linear equation. So we have everything equal to 0. And again, the next thing that's important here is to recognize, because we have a t squared, a t, and t to the 0 here, this is going to be a Cauchy-Euler equation. So for that reason, we're going to make a guess that looks like ct raised to some power r and see what happens. So I'm going to plug this back into the differential equation. So to do that, I need to take two derivatives. So the first derivative is going to be rc times t to the r minus 1. And the second derivative, I'm going to bring the r minus 1 down, so I get r times r minus 1 ct to the r minus 2. I plug this into the homogeneous equation. So t squared times the second derivative of the homogeneous solution is r times r minus 1 ct to the r minus 2 minus 2t times the first derivative, which is rct to the r minus 1 minus 4 times the homogeneous solution is ct to the r is all equal to 0, which comes from there. Let's clean this up. So I combine the t terms. This becomes t to the r. So this becomes minus 2r times ct to the r. And I'm going to leave the last term alone. And now I notice I can factor out a ct to the r. And I'm left with r times r minus 1 minus 2r minus 4 is 0. This ct to the r coincides with our homogeneous solution. We don't want that to be 0. So that means this thing in the braces has to be 0. So I have r times r minus 1 minus 2r minus 4 is 0. So let's multiply through the r. So I get r squared minus r minus 2r minus 4 is 0. Cleaning that up, I get r squared minus 3r minus 4 is 0. So what does that look like? R minus 4 times r plus 1, I think, is we can factor that. So I get minus 4 plus 1 is minus 3r, minus 4 times 1. Okay, so r is 4 or minus 1. Okay, well, let's see. What do we get? We get that our homogeneous solution looks like c1 t to the 4 plus c2 t to the minus 1. All right. So now let's look at the particular solution. So we go back to our original equation. We have t squared y double prime minus 2t y prime minus 4y is log of t. We know our homogeneous solution looks like c1 t to the 4th plus c2 t to the minus 1. So again, I don't know how to guess something for this. So what I'm going to do is I'm going to use variation of parameters. So my particular solution I'm going to say is u1 times t to the 4th plus u2 times t to the minus 1. And t to the 4th comes from the homogeneous solution t to the 4th, and t to the minus 1 comes from the homogeneous solution t to the minus 1. And I'm going to plug this into my particular solution and see what that applies about U1 and U2. And again, it's important to recognize we have two functions or two unknowns, so we need two equations. And after I take the first derivative, because of the product rule, I'm going to have four terms. Anything with a derivative of U1 and U2 in it, I'm just going to arbitrarily say those add up to 0, because the only thing I care about is whether or not this works in that equation. So the second equation I make up doesn't matter. So the first derivative, I'm going to use the product rule. So I'm going to have U1 prime t to the fourth plus 4U1 t cubed. That's the derivative of the first term. Derivative of the second cubed is U2 prime t to the minus 1. Then for the derivative of t to the minus 1, I'm going to have minus t to the minus 2 all times U2. I don't like that term, so I'm just going to let it equal 0. So U1 prime t to the fourth plus U2 prime t to the minus 1 is 0. And that means now my y prime is going to be 4U1 t cubed minus U2 t to the minus 2. So the second derivative now becomes 4U1 prime t cubed. 3 times 4 is 12U1 t squared. Then for this term, I'm going to get minus U2 t to the minus 2. And I bring down the minus 2, I'm going to get plus 2 U2 t to the minus 3. Plugging this into the particular solution. So I'm going to have t squared times y double prime. So that's 4U1 prime t cubed plus 12U1 t squared minus U2 t to the minus 2 plus 2 U2 t to the minus 3, which comes straight from there. Minus 2t times y prime. I'm going to use this term. I know these add up to 0, so that's going to leave 4U1 t cubed minus U2 t to the minus 2. And now I've got minus 4 times y, and that becomes U1 t to the fourth plus U2 t to the minus 1 equals log of t. Okay. So let's just expand all this out. So for this term, it looks like 4U1 prime t squared times t cubed is t to the fifth. I'm going to have plus 12U1 t squared times t squared is t to the fourth. Minus U2 t squared times t to the minus 2 is just 1. Plus 2U2 t squared times t to the minus 3 is t to the minus 1. For this term, I'm going to have minus 8U1 t to the fourth. I'm going to have plus 2U2 t to the minus 1. And then finally, for this term, when I multiply that through, I'm going to have minus 4U1 t to the fourth minus 4U2 t to the minus 1 all equals log of t. And anything here that does not have a derivative should cancel out. If not, a mistake was made. So notice minus 12 minus 8 minus 4 is 0. 2 plus 2 minus 4 is 0. Oops. This term should have a derivative in it. That came from there. So that's my y double prime. This came from there. So that came from that derivative. So that actually should have a U2 prime, which makes that U2 prime. And then that should be U2 prime. So I made a mistake there. So this is why it's so important to check your work, and so important to be neat and keep track of everything you have. So where does that leave us? We now have the following. We have our equation, t squared y double prime minus 2t y prime minus 4y is log of t. Because of that, we decided to use variation of parameters. Our homogeneous solution we decided was C1 t to the fourth plus C2 t to the minus 1. Our particular solution we decided was U1 times t to the fourth plus U2 times t to the minus 1. And our two equations, we plugged this into our original equation. We got two equations. First equation is U1 prime t to the fourth plus U2 prime t to the minus 1 is 0, which this is something we made up. Now when we plug back into here, we found that for U1 prime t to the fifth, I gotta be careful here, it looks like minus U2 prime equals log of t. Is that correct? I think we're okay. All right. So at this point, we just do a stop and reset. I'm going to use this equation to solve for U2 and then plug it into here. And we'll isolate U1 prime and U2 prime. So this says that U2 prime t to the minus 1 is minus U1 prime t to the fourth. If I multiply through by t, I get U2 prime is minus U1 prime t to the fifth. Okay. And now if I plug that into this equation, I get 4U1 prime t to the fifth minus U2 prime, so it becomes minus a minus. U1 prime t to the fifth is log of t. So adding those together, I get 5U1 prime t to the fifth is log of t. Sorry, U1 prime is 1/5 t to the minus 5 log of t. And then U2 prime is going to be minus that times t to the fifth, so I get minus 1/5 log of t. Neither of these are nice to work with. They're both going to be integration by parts. Let me do this one first because I think it's going to be a little bit more straightforward. So U2 prime is minus 1/5 log of t. Take the antiderivative of both sides. So we get U2. It's going to be the antiderivative of minus 1/5 log of t dt. So I'm going to do the trick. So I've seen an obvious way to do this. So I'm going to notice that there's a 1 here. I'm really multiplying this by, I can just think of it in terms of the minus 1/5. And I want to take a derivative of log of t because that becomes 1 over t, and I can deal with that more easily than the log. So let's make dv equal to minus 1/5 dt, which comes from those two things. Once I do that, everything else is going to be determined, because whatever left here is going to be what? Log of t. So the antiderivative of v is going to be minus 1/5 t. Derivative of log of t is going to be 1 over t dt. So this becomes u times v minus the antiderivative of v du minus a minus. Be careful here. Let me rewrite this because this is awkward. So this becomes minus 1/5 t log of t plus the integral of v du, or minus, but the minus a minus. So I get 1/5 t times 1 over t dt. All right, let me rewrite all this stuff out. So my particular solution I decided was u1 t to the fourth plus u2 t to the minus 1. I had u1 prime is 1/5 t to the minus 5 log of t. u2 prime is minus 1/5 log of t. And doing this one first, we got u2 is minus 1/5 t log of t plus the integral of 1/5 t times 1 over t dt. T divided by t is 1. So I get minus 1/5 t log of t plus the antiderivative of 1/5 dt. Now I can do that antiderivative. This becomes minus 1/5 t log of t plus 1/5 t plus a constant we'll call k1. So there's my u2, which I'm going to use later when I plug into that term. All right, u1 prime is 1/5 t to the minus 5th log of t, and I'm basically going to just do the same thing with integration by parts. So the antiderivative of the left-hand side is the antiderivative of the right-hand side. And again, I want to take a derivative of log of t because that's just going to be nicer. So that means everything else becomes my dv. And once I decide that, everything else is going to be determined. So that means my u is log of t. And so now the antiderivative of 1/5 t to the minus 5, so it's going to be what, minus 1/20th t to the minus 4th, is that right? If I bring down a minus 4, this becomes 1/5 t to the minus 5th. Derivative of u is 1 over t dt. So this is just u1 equals uv, so I get minus 1/20th t to the minus 4th log of t minus the integral of v du, but I get a minus sign there, that becomes plus 1/20th t to the minus 4 times 1 over t dt. Let's clean up that mess. First term I leave alone, plus, and we pull out the 1/20th. T to the minus 4th times 1 over t is t to the minus 5th. And now that integral I can do. So I get minus 1/20th t to the minus 4 log of t. So this, when I bring down a minus 6, and I get, that's going to be minus 4, t to the minus 4 plus c. So let me rewrite that. Minus 1/20th t to the minus 4 log of t. This becomes minus 1 over 80 t to the minus 4. I'm going to be careful here. I call that k1. Let's call this k2. So when we plug back into here, we don't get too confused. All right, so now my particular solution is u1 t to the 4th. So it's this thing. So I get minus 1/20th t to the minus 4 log of t minus 1/80th t to the minus 4 plus k2 times t to the 4th. Okay, plus u2 times t to the minus 1. u2 is this, so minus 1/5 t log of t plus 1/5 t plus k1, all times 1 over t. And so now, let's just rewrite that. So that's the first term plus the second term. And now I take that t to the fourth through, that's going to cancel, so I'm left with minus 1/20th log of t. Those are going to cancel, so I'm left with minus 1/80th plus k2 t to the fourth. Notice there's one of my homogeneous solutions. So if I do everything right, my homogeneous solution should pop out of here. If not, I did something wrong. So for this term, these t's cancel. So I have minus 1/5 log of t. Then 1/5 t times 1 over t is plus 1/5. And I get plus k1 times 1 over t. And again, that's my other homogeneous solution. And, oh gosh, that's a mess. So let's see. On a quiz or test, you could just leave it here. That's fine. I'm just going to collect terms. So my common denominator here is going to be 20. My common denominator here is going to be 1 over 80. Leave that term alone. So if I multiply top and bottom by 4, now I need 80. Great. So that's going to be 80 divided by 5 is 16. So multiply top and bottom by 16. Let me rewrite 1 over t as t to the minus 1. So this becomes minus 5 over 20 log of t plus 15 over 80 plus my homogeneous solution. And there is my particular solution. All right, one more example. Let's go t y double prime plus y prime minus 3 over t. Oh, nope, that's going to be 1 over t times y is t e to the t. First thing is to recognize this is Cauchy-Euler, but it's not Cauchy-Euler form. If I multiply everything by t, I get t squared y double prime plus ty prime minus y is t squared e to the t. So now it's in Cauchy-Euler form. I'm going to do, and yuck, I have no idea what to guess for this, especially with these t's. So I'm going to use variation of parameters. Notice on a quiz or test, it will not be clear at all what you should use, just because you won't have the context of what we're doing at the time. So it's important to stop and make that decision. So for my homogeneous solution, I'm going to guess c times t to the r, and my homogeneous equation is going to be the thing I have above, I just set it equal to 0. So I need to take my guess and take two derivatives. So the first derivative is r times c times t to the r minus 1. Second derivative is r times r minus 1 times times t to the r minus 2. Plug it into my differential equation, in this case the homogeneous solution. So I get t squared times the homogeneous solution. This should be y double prime. Times r minus 1 ct to the r minus 2 plus t times the first derivative. So that's r ct r minus 1 minus the homogeneous solution, all equals 0. Let me combine the t terms. So this becomes t to the r. This becomes rct to the r minus ct to the r. Every term has ct to the r. If that does not happen, you made a mistake. So what's left is r times r minus 1 plus r minus 1. This is my homogeneous solution. It's not 0, so that means that all needs to be 0. So we get r times r minus 1 plus r minus 1 is 0. Multiplying this r through, I get r squared minus r plus r minus 1 is 0. The minus r plus r cancels, so I get r squared minus 1 is 0. R squared is 1, so that means r is 1 or minus 1. All right, so what do we have at this point? Going back to our particular solution, and I'm looking for it in Cauchy-Euler form, t squared y double prime plus ty prime minus y is t squared e to the t. My homogeneous solution, so r was 1 and minus 1, is c1 t to the 1 plus c2 t to the minus 1. I don't know what to guess, so I'm going to use variation of parameters. So my guess is going to be some u1 times t, which comes from there. u1 is a function of t, plus u2, which is a function of t, times the second homogeneous solution, which looks like this. I'm going to plug this into the equation. But I got to be careful here. I got to use the product rule because u1 and u2 are functions of t, and I'm multiplying. And I'm going to make up the equation to get rid of the derivative terms after the first derivative. So yp prime is going to be u1 prime t, derivative of t is 1, derivative of u2 is u2 prime, and the derivative of t to the minus 1 is going to be minus t to the minus 2. This term plus this term I'm going to force to cancel. So I'm going to just make that equal to 0, which means then my yp prime becomes u1 minus u2 t to the minus 2. So now for the second derivative, yp double prime is going to be u1 prime minus u2 prime t to the minus 2. Derivative of t to the minus 2 is going to be, bring down the minus 2, so minus a minus 2 t to the minus 3. So I get t squared. So I'm plugging back into my particular solution, times the second derivative is u1 prime minus u2 prime t to the minus 2 plus 2 u2 t to the minus 3 plus t times y prime. So that becomes u1 minus u2 t to the minus 2, which I'm getting from here, minus y, which comes from my definition, is u1t plus u2 times t to the minus 1, all equals t squared e to the t. So let's multiply everything through. So I get u1 prime t squared. T squared times t to the minus 2 is 1, plus u2 t squared times t to the minus 3 is t to the minus 1. Multiplying through my t there, I'm going to get plus t u1 minus u2 t to the minus 2 times t is t to the minus 1. And then here I'm going to have minus t times u1, which is coming from this term. And then here I'm going to have minus u2 t to the minus 1, all equals t squared e to the t. I'm hoping lots of things cancel out. Those cancel. Those cancel. Oops, sorry. I need that. So 2 minus 1, leaving only that term. So my second equation is u1 prime t squared minus u2 prime is t squared e to the t. Let's rewrite all that. So I had my particular solution is u1t plus u2t to the minus 1. My homogeneous solution was c1t plus c2t to the minus 1. My two equations now are u1 prime t plus u2 prime t to the minus 1 is 0. And I just found that u1 prime t squared minus u2 prime is t squared e to the t. this has worked out well so far. I'm going to solve that for u2. So u2 prime t to the minus 1. I subtract u1 prime t from both sides, multiply both sides by t, and I get u2 prime is minus u1 prime t squared. Okay, so let's plug that into here. Get u1 prime t squared minus u2 prime, so minus a minus u1 prime t squared is t squared e to the t. Pulling those together, I get 2, 1 u prime t squared is t squared e to the t. Divide out the 1/2, divide out 2t squared, and I'm going to get 1/2 e to the t. So those are my two equations. Let me see. And then plugging into here, minus u1 prime t squared, I'm going to get a minus 1/2 t squared e to the t using that result. All right, this one's going to be easier, so let me do that first. So I have u1 prime is 1/2 e to the t. I take the antiderivative of both sides. I get u1, antiderivative of e to the t is e to the t plus, oops, let me go with k1. So there's my u1. u2 prime is minus 1/2 t squared e to the t. I take the antiderivative of both sides. Oh, great, okay. I can take the antiderivative of e to the t without any problems. And if I take the derivative of t squared, it becomes a t. I like that better. So that this is going to be my dv, and this is going to be my u. So I get the antiderivative of u2 prime is u2. And what did I just say? I said that my dv is going to be e to the t. All right, once I do that, that defines my u. So it's everything that's left. And now I just got to follow through. So antiderivative of e to the t, be careful, that's dt, is e to the t. Derivative of minus 1/2 t squared is going to be minus t. So uv is minus 1/2 t squared e to the t minus the antiderivative of v du. I got a minus there. T e to the t. Okay. You rewrite all of this. My particular solution, I said, was u1t plus u2 t to the minus 1. And I have now that u1 is 1/2 e to the t plus k1. u2 is minus 1/2 t squared e to the t plus the integral of t e to the t dt. Again, I can take the antiderivative of that, and I want to take a derivative of t because that'll be nicer. So that means my dv is e to the t. That means whatever is left is u. So that's my t. I gotta be careful, this is dt. Antiderivative of e to the t is e to the t. Derivative of t is 1. So u2 becomes minus 1/2 t squared e to the t. Just bring that down. This becomes uv, so I get 2 e to the t minus integral of v du, which is e to the t dt. Now I can do that integral. So finally I get u2 is minus 1/2 t squared e to the t plus t e to the t minus e to the t. And then I got to be careful, I need a constant of integration. So my particular solution is u1 times t. That is 1/2 e to the t plus k1 all times t plus u2 times t to the minus 1. That's minus 1/2 t squared e to the t plus t e to the t minus e to the t plus k2 times 1 over t. So that becomes, so multiplying this t through, I get 1/2 t e to the t plus k1t. Oh, there's a homogeneous solution. I like that. multiplying this 1 over t in, I'm going to get minus 1/2 t e to the t. This is going to give me an e to the t, and minus 1 over t e to the t plus k2 times 1 over t. Cleaning this up, those two things cancel, and that's the only like term I have. So it gives me e to the t minus 1 over t e to the t plus k1t plus k2 times t to the minus 1. There's my homogeneous solution. There's my particular solution. And notice there's no way you're going to make a guess like that for the solution to this thing.